All right, so as I said, Chapter 6, we're not going to do a ton of the things in Chapter 6, and now we are going to jump ahead and look at a few ideas from Chapter 7, and next week you're going to have a test on the ideas from 6.1, 6.2, 6.5, and now 7.8. So again, just give you the heads up, you have a test next week on Chapters 6 and 7, just those select areas that we've gone over. So 7.8, I'm going to break into two separate lessons. This is our first one, and we're going to be introducing the idea of improper integrals. So get yourself ready for notes, and we're going to get started. Now, improper integrals, one type that you'll see here, this first type is where you have an infinity in one of your bounds. So, improper integrals. They basically, you could think of it as they have an issue with their bounds. So the first issue that you'll see is one bound or both is equal to plus or minus infinity. So you could have a positive infinity, a negative infinity here. But the idea is for most of these, most things, if we're adding up the area as x goes towards infinity, we're going to end up with just a really big or really small number. The area is going to get just huge, and it'll equal infinity. However, there are some problems, such as the one that we're looking at, where the function, this is e, the first one, e to the negative 2x, it's a negative exponential function. So it's going down like this, and when we're adding area as x approaches infinity, right, this is our infinity we're approaching, the area under the curve is getting smaller and smaller and smaller and smaller. So the area might actually, what's called converge, meaning that it goes to a number. So the horizontal asymptote is necessary. And it has to be at y equals 0. So you have to have that to be true. If you don't have this nice horizontal asymptote where the area under the curve is getting really, really, really small, it's just going to equal positive or negative infinity. So if the integral equals positive or negative infinity, we say that it diverges or is divergent. Now, it also might converge or be convergent, and we're going to, in this case, we'll have to go through our integral and see, since it does have this horizontal asymptote, the area might get small enough that it approaches a number. So here we have the integral 0 to infinity of e to the negative 2x dx. So the way that I am going to choose to integrate here is I'm going to use u substitution just to deal with that coefficient in the exponent. So then I get du dx is equal to negative 2. And since I only have a dx here, I'm going to solve for that, and I end up with negative 1/2 du is equal to dx. We also can change the bounds. When I plug 0 in, so this would be negative 2 times 0, negative 2 times infinity, like so. We get e to the u times negative 1/2 du. I am going to take the coefficient, pull it forward. So negative 1/2. 0 to negative infinity now, just changing those bounds of e to the u du. The antiderivative of e to the u is just e to the u, so negative 1/2 times e to the u from 0 to negative infinity. Set up the difference, negative 2 e to the negative infinity minus negative 1/2 e to the 0. Now here what we want to do is, we can't necessarily plug in infinity, but you want to just treat it like a limit. So we know that the limit as x approaches negative infinity of e to the x, we can think about it as evaluating like that. Since this will equal 0, it converges. So we can say that that is negative 1/2 times 0 for e to the negative infinity, plus, I'm just simplifying those negatives there, 1/2 e to the 0, which is 1. So this improper integral converges because it equals a number, and that number is 1/2. So all this area under the curve here is equal to 1/2. So let's look at another one. Here we have 2 to the negative infinity of 1/1 plus t squared dt. Now the main thing here is we need to recall the antiderivative of this function. It looks a little unfamiliar, but if we remember, the derivative of tan inverse of t is equal to 1/1 plus tan t squared. So this is just a unfamiliar derivative, but you will see it show up a couple times here. Now, there's no u substitution needed. This is just the same as that function over there. So the bounds can stay negative infinity to 1 of 1/1 plus t squared dt is equal to tan inverse of t from negative infinity to 1. Now, tangent inverse does have horizontal asymptotes. If I graph out this function, tan inverse looks like this with a horizontal asymptote here and a horizontal asymptote here. It's one of the reasons they are used a lot in improper integral problems. So here's our negative infinity, positive infinity, and this horizontal asymptote here is negative pi/2. You may run into this one later, hint, hint, that's positive pi/2. So since we're going, if we think about this as our limit of tangent inverse of 1 minus tangent inverse of negative infinity, looking at the limit for this, we can see that it is negative pi/2, and tangent inverse of 1 is where the tangent function is equal to 1, which is pi/4. So then pi/4 plus pi/2, this also converges to 3pi/4. So we have two different types of convergent improper integrals in these examples, and we will look at the other type tomorrow. So good luck on these problems, and if you're stuck, please let me know.